The fact that you are watching this video shows that you want to know what entropy is. In fact, it must be admitted that usually such attempts leave behind an annoying feeling of not understanding. This is due to the lack of a proper interpretation of the meaning of entropy at the microscopic quantum level. I will try to present a fundamentally new explanation as clearly as possible. The truths of the quantum nature of entropy have been published recently in our articles. Links to all the articles are provided in the description of this video. This video and our articles will be especially useful for students who have a desire to truly understand what they are studying. And by the end of the video, like the cherry on top, we'll be presented with something truly astonishing regarding the currently accepted quantum interpretation of entropy. So fasten your seatbelts. The discussion about the meaning of entropy should begin with Boltzmann's outstanding article, published in 1877 in the journal Wiener Berichte. This article examines the distribution of energy among the molecules of an ideal gas, when the interactions between molecules can be neglected. Boltzmann denotes the total number of gas molecules as N, and the number of molecules with energy, E sub k, as W sub k. Each distribution can be realized in various ways, which Boltzmann calls complexions. The number of complexions in a distribution equals the number of permutations of the molecules. Formula 1. Boltzmann showed that thermal equilibrium in a gas corresponds to the maximum number of permutations. In this case, the probability of a molecule having energy E sub k is given by Formula 2. The logarithm of the maximum value of P, Boltzmann, up to a certain constant, identifies with the entropy of an equilibrium gas. Formula 3. It can be considered that the complexes characterize the microstate of the gas, and their number is denoted as W. If we replace P maximum with W, we obtain Formula 4. Here, K is the Boltzmann constant. In our articles, we search for the most probable distribution of quantum states in systems consisting of a macroscopically large number of interacting particles. The Boltzmann method is impossible to apply it directly to such systems. However, Boltzmann's remarkable paper greatly helped us to find a quantum-level justification for the interpretation of entropy. Now, I will explain how we managed to achieve this. According to quantum mechanics, the total energy of a physical system is given by Formula 5. Here, En is the value of the energy in the system spectrum. According to quantum mechanics, the squared modulus of Cn determines the probability of the energy value being equal to En. And now, attention. It only makes sense to talk about the probability of a particular state with energy En when the system transitions from one state to another. Therefore, the squared modulus of Cn is the probability of the system being in a state with energy N. It should be noted that quantum mechanics says nothing about transitions between states with different energy values En, nor about the processes that cause these transitions. However, without taking such processes into account, all discussions about probability in quantum mechanics become meaningless. We will refer to the level of organization of matter at which these processes occur
as
subquantum level. It is precisely subquantum processes that are responsible for the emergence of a system's state with energy En. Anyone even slightly familiar with probability theory will agree with me that Formula 5 can only be used when there is a very large number of transitions from one state to another during the observation period. This means that subquantum processes occur extremely rapidly, and to describe them, the timescale we are accustomed to would be inconvenient. The processes of the emergence of a state with energy En are also not discussed in statistical physics. In our works 1 and 2, it was shown for the first time that the canonical distribution and the entropy of a system are a consequence of subquantum processes. The emergence of a system state with energy En, or the end state, is referred to in these works as the system visiting such a state. The total number of these visits over a certain period, or observation time, and the number of visits to a specific En state during this time are denoted as N and Vn respectively. Those knowledgeable in mathematics will confirm that the same energy value is possible with various distributions of the quantities Cn by modulus squared in Formula 5. Subquantum processes occur in accordance with the law of conservation of energy. That is, they preserve the total energy of the system. Each distribution of the values of Cn by modulus squared corresponds to a certain set of visit numbers, which we call a configuration of visits, or simply a configuration. Each configuration can be realized in ways corresponding to the number of permutations of visits. Formula 6. It is easy to see that Formula 6 is similar to Boltzmann's Formula 1. In our articles, it was shown that the largest number p corresponds to the configuration in which Vn is given by Formula 7. From which we obtain Formula 8. Formula 8 is the canonical distribution formula for the probability of an energy value
of a macro system.
The calculations carried out in the articles we published led to Formula 9,
where ρ from E is obtained by substitution,
and with E in Formula 8, that is expressed in Formula 10. Using well-known relations from classical thermodynamics, in Article 2 we demonstrated that minus the logarithm of R of E equals the entropy of system S. Accordingly, we have Formula 11. Formula 11 means that
Entropy is expressed as the ratio of the logarithm of the maximum number of realizations during the observation period of the configuration corresponding to the canonical distribution to the number n of occurrences during this time of all states with energy En.
Let us emphasize that Formula 11 is a strict mathematical result. Boltzmann's Formula 3 characterizes the entropy of a gas in a state of thermal equilibrium. In the general case, the entropy of a gas is represented by Boltzmann through the logarithm of p, where p is given in Formula 1. Following Boltzmann, the entropy of macroscopic systems in the general case can be defined by Formula 12. Where p is given by Formula 6. In this case, the energy of the system can be expressed by Formula 5. Calculations similar to those performed in work 1 yield the formula that you see on the screen. Irreversible evolution caused by subquantum processes brings the macroscopic system to a state of thermodynamic equilibrium with the maximum value of p. That is, to the maximum entropy. Well, and now for the cherry on top. In statistical physics, entropy S is related to the number W of quantum mechanical states by Formula 13. It is asserted that the quantum mechanical energy levels of the system are concentrated within an extremely narrow interval around the point E, where E is the total energy of the system. See, for example, the textbook on statistical physics by Landau and Lifshitz. How this assertion leads to Formula 13 is shown in our Article 2. Let us now examine the vicinity of point E. According to statistical physics, the total energy of a macro system, or simply its energy, is given by Formula 14, where rho of n is defined by Formula 8. The energy E of the macro system, depending on the temperature, can take various values within the spectrum of the system. However, the spectrum of E values itself does not depend on E in any way. Therefore, the assertion that the energy levels of the system belong to an extremely narrow interval in the vicinity of point E that must fluctuate along with the values of E has nothing to do with physical reality. Entropy cannot be equal to the logarithm of the number of states that do not exist. How Formula 13, with its shocking interpretation of the quantity W, made its way into quantum physics remains a mystery. Perhaps the reason was the desire to obtain a formula similar to Boltzmann's Formula 4. I hope that my explanation will help you better understand the physical meaning of entropy, one of the most important characteristics of the phenomena of the world around us. It would also be helpful to read our Articles 1 and 2. They are freely available on the internet. You can see my email on the screen. It is also listed in the description of this video. I will be happy to answer your questions, and students can discuss this video with their teachers. I think such discussions will be very productive. You might ask, if you are so smart, why haven't you published your theory of entropy in a prestigious journal, for example, in Nature or Science? Look up on Google what Nobel laureate Randy Schekman thinks about these journals, and everything will become clear.